on to quote unquote the CPU solver. This is just, I guess, looking at some features that are actually just brand new to Fluent. Everything else that we've been looking at so far has just kind of been stuff from the main solver that's been rewritten into the GPU solver. So let's have a look now at some actual new additions. Just quickly on heat transfer, I've just got one slide here. Anyone that likes to use like shell conduction, that kind of thing, you might have found that in the past it's been limiting in that you can't have a variable thickness through your layer, or you can now use expressions there to have a variable wall thickness. So say you've got, I don't know, like an insulating layer between two solids or something. Maybe there's like a plastic insulator, and maybe that's not perfectly uniform, or you can now specify that with an expression to have that varying thickness. Onto electrochemistry. So something that we've had for a while in Fluent has been thermal abuse for batteries, but that was kind of limited to the cell itself. And what can be, what a limitation of that is say you've got a whole pack of cells and maybe one of them gets damaged, it gets thermal runaway. What tends to happen in reality is that cell can burst and essentially ignite a bunch of combustion reactions, which then sort of spreads the thermal abuse of thermal runaway to all of the other cells. So the only way to sort of model that is to actually provide a mechanism to have that combustion. So it's a sort of semi-empirical model here, and there's a combustion mechanism that is built in that handles sort of a well-rounded default case. I believe you can also bring in your own mechanism if you have particular chemistry that you would like to solve, but by default there is one in there, so you don't have to worry about chemkin or anything like that. It is built in. But yeah, essentially there's like a correlation between the amount of thermal abuse that's happening and the amount of gas that is going to be vented from a broken cell, and that then sort of lets the combustion form and therefore go on and damage the other cells there. I don't know if did that video play? Yeah, you can hopefully kind of see that occurring where there was like a nail strike or something in the first cell, and as the combustion has taken place, it sort of spread through the whole pack. Also on the topic of batteries, we can now do immersion cooling with multiphase. So previously, you could have surrounded your battery pack in water and you would have the immersion cooling effect, but it maybe not massively physical because it wasn't able to boil. So that's now in there. So you can see here we've got a model that, again, I might just replay the playing. I think they are. Maybe not. Yeah, it is. Okay, so what that was is essentially, it's been immersed in a liquid. As the liquid temperatures approach this boiling point, it's then boiled, and we have like a big step change in the cooling performance as a result of that boiling effect. Another one here onto fuel cells now. So there's an addition now to be able to do cold start modeling for fuel cells. So this is essentially, the condition where there's ice inside the device. So that startup period has to account for that ice melting. So that's now possible to solve in Fluent. Onto electrolysis, there's been quite a few improvements in the electrolysis space. Just two examples here. One is sort of this effect you can get when you have water condensing on the cathode that's now sort of accounted for. One that's actually quite useful to anyone trying to do these as well is this 0D approach. So when you're doing a fuel cell or an electrolyzer, you have quite a few layers through your device, and meshing through all of those layers can result in a massively, just a huge mesh, right? Takes forever to solve. So there's now ways that we can sort of handle some of those layers, the catalyst and the membrane layers, without a mesh. They're kind of just acting as like a interface layer instead. And the last one here on electrolysis, I'm not going to go through the details of what this is, what I'm going to say is high level on this slide, which is that the electrolysis model, when it first came in a couple of years ago, very, very rigid, right? It needed to work on a very specific type of geometry. If your cell looked different to that specific geometry, you pretty much couldn't solve it. So the theme here is that it's now far more flexible, far more customizable. And I'm just going to put in a plug for my colleague, David Fletcher. He is like at the forefront of doing this like globally. He's working really, really closely with Ansys, with a few customers that we've been taking on recently. So if you're trying to solve electrolysis and you want help, please reach out to us, and David Fletcher will be more than happy to take a look at it for you. Alrighty, onto aerospace. I'll start with some high-speed flows, so the density solver in particular. There's been an update to solution steering. Anyone that has used solution steering in the past, you might have found it's a little bit clunky. The solution steering, by the way, is just it's kind of like a adaptive time stepping type thing. So you can tell it to start with like a really, really small current number, and then as the solution stabilizes, it'll ramp up to a higher current number and get through your simulation more quickly. So there's been some improvements there. There's also a few little numerics things, particularly when symmetries or periodic boundaries are involved, just getting rid of some sort of spurious behavior. Oh, I lost my laser pointer. So yeah, you can see like along this symmetry plane here, particularly for heat fluxes, so like derivative quantities, kind of had some unphysical values on these symmetry or periodic boundaries that's now been accounted for. The virtual blade model is now available in the density-based solver. Just to quickly explain what the virtual blade model is, rather than having your helicopter rotors physically there in geometry and rotating, which is quite an expensive thing to do, you essentially just put a disk in there instead, and that disk sort of has momentum sources that act like your blade, so long as it has been characterized first. That's now available in a density-based solver, and it can be used in transient simulations now as well. Now, that's not to say that it's going to be capable of doing like proper rotor-stator interactions. Of course, a momentum disk is not a replacement for full blade geometry for doing that kind of work, but it does mean that it can respond to changes in boundary conditions, essentially. Within the Fluent Aero workspace, mesh adaption's now in there. I mean, anyone outside of the Fluent Aero workspace, you've had access to this already, but it's good to now see this in sort of like the guided workflow mode that is Fluent Aero. And one thing that I thought was pretty cool is it's now got a new sort of automatic search for finding the stall angle of attack. So it'll run through range of angles of attack at any given operating condition, and we'll sort of keep playing with it until it finds the stall angle for every operating condition. So that's a nice thing to have, to not have to work out manually. Onto turbulence modeling. I've just got two slides here. One of them looking at RANs, and then the other will be on LES. But just quickly on the RANs front, I don't know if anyone in the room uses Gecko yet. It's essentially, in default, guys, anyway, it's essentially K-Omega SST, but it's got some sort of free coefficients that you can tune that are physics-based. So what I mean by that is there'll be a coefficient for separation, right? And there'll be a coefficient for mixing behavior. And what that lets you do is tune the model based on the physics that you're trying to represent, rather than tuning some arbitrary constant in the model that's going to have knock-on effects and ruin the behavior or the performance in some other aspect. So it's been around since 2015, but as of 2024, it's kind of beta. So I guess the full release of it will be next year. There's an updated version that just does an even better job of splitting out those physics-based coefficients. And then just onto the LES front, there's a new formulation for wall-modeled LES that is more Reynolds number insensitive. So previously, if we were to look at this graph, I probably should have had a comparison, but you would see that at different Reynolds numbers, it would follow the wall model better than at others. So now this is just showing that regardless of Reynolds number here, we've got quite a range from 400 up to 18,000, that we're getting really consistent performance across those Reynolds numbers. Onto solver meshing. So when I say solver meshing, I mean things like dynamic meshing. that happens within Fluent. I'm not talking about meshing that happens up front. We'll go on to that a little bit later. Back to the topic, I guess, of acoustics. Overset mesh is now compatible with acoustics, which is really good. Quite often I'll see overset being used for propellers. Quite often also used for like boat propellers as well. I'll have an overset mesh in there, and it's good to see that that's now compatible with acoustic workflows. There's now a new local smoothing option for radial basis function dynamic meshing, and I won't go into massive details of what it actually means, but what you can see here is the result is that like the background mesh where the movement is not occurring, I'll just replay that. The background mesh is like super static, but we're keeping all of our mesh refinement around our main object, right? The boundary layers are moving with it really nicely. The surrounding higher resolution mesh is moving really, really smoothly with it as well. So that's a nice feature to have in there. Onto the performance side of things, for cases where you've got lots of non-conformal interfaces, it's much faster now in 24R2. And we've also got an adjustable tolerance for one-to-one interfaces. So say you've got an interface where there's a little bit of a gap. I don't know, maybe the mesh isn't 100% perfect. Maybe the geometry isn't 100% perfect. You can now tell it to tighten that tolerance, to loosen that tolerance a bit to get you sort of better one-to-one mapping across that interface. There's a new geometry reconstruction framework here. So anyone that's modeled anything like an airfoil before, or the Formula SAE teams, I'm sure you see this quite a bit, where you're trying to balance your mesh count versus actually getting that nice curvature of, say, a leading edge. And you quite often might end up with a mesh a little bit like this, which is not going to give you the most accurate separation behavior. So it's now possible to like bring the geometry itself through to Fluent and dynamically remesh to improve that mesh for a leading edge or for a trailing edge or something like that within the code. And another random little feature that you may or may not ever find a use for, but you can now delete cells on a cell-by-cell basis as well. Motion definitions, I'll just very quickly talk to this. So with dynamic meshing, you'll quite often see that you need to make a motion definition somewhere. You quite often use a UDF for it. There's now, like within the GUI itself, a new way of handling these motion definitions that's really, really clear, and you can make multiple of them and have them all sitting there, easy to edit. Just onto the adjoint solver. I think I've got 2 slides on this. It's got some improvements to expression handling. So if you wanted to make sort of more advanced observable, it's now able to handle more advanced expressions in there. And one of the newer features in this release is goal-based mesh adaptation. So say you're trying to do a mesh independence study, rather than like remeshing your problem every single time, like manually, or say running a script that goes through all these different mesh adaptation loops, it's now possible to use the adjoint solver to work out where some refinement is required, and you can tell it to follow a particular goal. So in this case here, you can see that we've got this reference case. It's a really fine mesh, 9 million cells just for an airfoil. And if we have a look at this baseline case underneath it, it's only 35,000 cells, like significantly smaller mesh, or coarser mesh, I should say. And with this goal-based mesh adaptation, you can see that it's trying to target the lift from that high resolution case. Doesn't quite get there, but does a pretty admirable job considering it's only using 63,000 cells versus 9.18 million. And the adjoint solver is now exposed to the Python API. We'll have a look at the Python stuff in a bit. I'm going to do a little bit of a demo on that, not on adjoint, but just to show that that's now available in there, and web UI as well.